Okay. Basically, I'm going to talk about sailplane design, kind of my evolution over a period of almost 30 years, mostly with cross country. And I got into cross country about 1990. I got it by a guy named Julian Tamez in Texas who had gotten it from Joe Wurts, and it was word of mouth, copied what he had done. So you can see that the two white planes in these pictures are a copy of Joe Wurts' Wiley's Revenge airplane, and he basically won everything that he ever showed up to it. They're very simple, F374, simple fuselage. Here's one that I built in Florida in a one-bedroom apartment with a hand tool. This one I built with my friend Noel in Los Angeles. It was a little bit better. Actually, this one still exists. I sold it to a guy in Australia. We did win a fair number of races with those. I got my level 5 with these two airplanes. They're probably not competitive now, but they're not bad. I decided that I wanted something easier thermal because I wasn't getting out on the course. So I went big and thermally. 70-37 airfoil, which was the rage at the time, 176-inch wingspan. I think I built this one in Florida also. That thing thermaled really well, but like I said, it wouldn't get out of its own way. I did get on course with it a couple times in Oregon. It's not as competitive up there as it is down here. I don't remember winning, but we did get around. So it was okay. It was not a bad airplane. But again, it was just pencil and paper. 70-37s were guys were flying, so I just kind of scaled up the Falcon 880 and made that. I got some early help from Joe Wurts. These two yellow airplanes here were kind of a transition. This one was MH32 airfoil from Germany. This is Joe Wurts' DS-19, DS-21, which are kind of slope, aerobatic DS airfoils, but he said they would work well in cross country. But basically, we were just making the plane. These were big airplanes, 176-inch span again, and it was like make the airplane and then fly it to fit the task, whatever the task was. Structurally, we learned that. Like this one had a spar in it and it survived. This one did not have a spar. I was going with a sparless construction, and if you cut the holes out for the servos, it's a weak spot, and we blew that one out. We used a clever wing design macro. I think the name of it was, there were two of them. One was called Ellipse, and I can't remember the other one. They won't run on the modern Excel. The last time I tried it, which was several years ago, so I think they're lost to the dustbin of history. But they were nice airplanes that would tell you, given a certain span and target wing area and wing load, it would tell you what the poly brakes should be for your foam cuts to get the elliptical wing lift distribution. These airplanes flew really well. One of these I did 66, no, one of these I did 92 miles with. I think this one right here. So they weren't bad. We won a fair number of races. It all depends on what you're up against, but it gets more competitive all the time. After we blew that one up, I decided to go simple, no cutouts for servos, 2-channel, polyhedral, same airfoils, but big cord. This was a 14-inch root so that we could see it really high. And again, that's just guesswork, but it's the direction R&R was going in at the same time, so we kind of were following a trend. I think I used the analysis program to design the wing, but I picked the airfoils again from Joe. And there was one year I took this airplane up to Montague with Joe Wurts on the sticks, and we won everything. But it depends a lot on who's flying.
No way.
After that one got splattered across the desert when I loaned it someone for a level 5 attempt, which is okay because it was nearing the end of its useful life. I got into this one, XC number 8. And there was a thread kicking around in RC groups that Mark Joel was designing a cross-country plane based on the Bubble Dancer. It was a very interesting design. He's very, very thorough. very experienced, takes every step of the design as far as you can possibly do it with the technology. What he did not know is that you have an unlimited start height. So he went with a smaller airplane, thinking you had to enter at a certain height, which is like, I guess, about that from full scale. Which would work, his airplane would work in those rules, and it was actually pretty competitive, but it's not going to work for what we were trying to do, which is fly really high. So I scaled it up to something that looked about in the right range. The sizing was based on guesswork, based on how high we'd flown the 14-inch root cord and what we were up against, and balancing wing loading versus size, but not getting into any real math yet. But trusting Mark Drela and his airfoils. This one I did publish on RC Group. Did I? Oh, I don't have a picture of it. Okay, it's on RC Groups though. It looks a lot like this one, except it's white on top and it's a T-tail. XC10. This is where I get help from the heavyweights. And I got help on this one from Joe Wurts, Mark Drela, and Phil Cole. So I had a chance meeting with Joe Wurts at Davenport, and he revealed this big step in educating me about how to go about design. You don't design the airplane. You model the task. And then you figure out how to run an airplane through it, and then you just start running different designs through the task, and the right one pops out the other end. So it took a while for me to really get this concept, like how do you model a task, what are you talking about, just give me an airfoil, I cut an airplane out. And he's like, no, you got to think of it the other way. And the thing is, once you learn how to do this, you can apply it to any airplane, any task, and it automatically steers you in the right direction to the good design. So how does one model a cross-country race? This is where I really kind of had to put the thought into it. And basically all he told me was I use an Excel spreadsheet, you're on your own. But a race is nothing but distance and time. So you figure out all the things that add up to distance and time. Make a mathematical representation of each one, and then figure out how the aircraft design affects each one of those items. Then you design an airplane. Where do you think it should be? You plug that design into the course, see how long it takes to fly from one end to the other. Then you can make a smaller one and try it. Does it get better or does it get worse? Make a bigger one and try it. Does it get better or does it get worse? And you're not really designing the airplane, you're just plugging it in, seeing how it does it versus the other ones. So what inputs can affect the time to finish? The climb rate. You got the climb rate of the thermal. Where do you get that? You get it from GPS data from your logger. We have hours and hours and hours of race data that was sitting there waiting to be used. So I just pulled it out of the logger and measured an average of 10 or 15 different thermals that we climbed up in, and came up with an average of how fast is that air actually going up when you hit it on course. The aircraft sink rate. How do you know what the aircraft sink rate is? Well, John Elliott down in LA did some tests with his SBXC where he put a logger in it and threw it in dead air and measured it 10 or 15 times in a row and calculated his measured L over D and sink rate. So now you have a reference design that you can plug into an analysis program and model and say, okay, I know the sink rate is X. So if I make another design and it's better or worse, you can compare it to his data and it gives you a hard number you can use, just as a comparison. Nothing is absolute because you can't model like every last fitting and control surface cutout and effect of a different fin or anything like that. But you're basically bracing one wing against another and seeing, is this one faster than that? What's the sink rate of the air between the thermals? That's another thing you can get from the GPS data on the course. I know, based on John's measurements, what's the sink rate of the airplane. Now I can measure what the altitude was when I left this thermal, what's the altitude when I got to the other one, and how fast was I flying, And it's just basic geometry. What's the sink rate of the air itself? So now I have a number for the air that's going up. I have a number for the air that's going down. I have numbers for the sink rate of the airplane. And I have L over D from John's data for one reference design airplane that I can use as a reference. One other thing that's important is the max altitude. How high can you fly it? That depends greatly on the chord. So I dug around on the internet and got some theoretical tests that some professor had done on sign visibility at a distance. And based on that data and some GPS or some Vario logger data that I had gotten, basically I know how high I can go with a given chord. So you can plug that in as a fixed value. So you have a 10-inch chord, okay, now I have to start here. If I have an 11-inch chord, I can start a little bit higher. A 12-inch chord, I can start a little higher. The thing is, every time you go up in chord, you're going down in wing loading, so you're paying a price. That's the beauty of this. Once you have the course model, you can vary all these things, plug it in, and it gives you a time it takes to raise to the end of the chord. What do you do about velocity? The wind speed, we have historical data. So you can plug it in. 5 meters per second, 8 meters per second, 10 meters per second. What's the effect of that? And then the speed on the course. How fast should you fly on the course? This is where the real heart of all this is. That was the real challenge that I spent several months digging and reading PhD dissertations and papers and formulas and stuff. And there's something called speed to fly. That's the hardest thing to figure out. And then there's this thing called McCready ring, which I don't really understand, but you can't put that in your model. But it's based on the math. It's just based on math. And given a known climb rate, sink rate, distance between the thermals, headwind, there is actually a formula that tells you what's the best speed for you to fly, given this airplane, to get from point A to point B and be there at the least loss of altitude and the fastest rate. So in order to get that, you need to have a polar of the aircraft. This is a polar of the aircraft. Basically, it's the bottom axis is Vx, which is your horizontal velocity, and the vertical axis is Vz, which is your sink rate. So if you look at this polar, like this point right here, when you're floating, this is the minimum sink. That's where you want to be when you're thermally. That's where you want to be if you decide you're going to float on good air down the road. If the air is going down the road with you, you just put it in minimum sink and float down the road and climb the whole way. But this here is a parabola, essentially, if you can imagine the other side of it over here, more or less. So what's a parabola? It's nothing but coefficients and expressions in a mathematical expression. So what you can do is take those points and you get a curve fitter, which I grabbed off the internet, and you can model this curve. There it is. This curve as a parabola using all these points that this program will spit out for you. And it gives you these coefficients, A, B, and C. And basically, what the polar is telling you is you can fly anywhere on this line. So if I want to go faster, going to the right, I'm going to pay for that in sink rate. So I can fly here, fly a little faster, I sink a little faster. I can fly here, I fly a little faster, yet I sink a little faster. I can go way up here, and I'm flying really fast, but I'm coming down really fast. So this is basically telling you where you can fly, it's just where you trim your elevator. And speed to fly tells you where on this curve you need to be to get from one thermal to the next through the sink, through the headwind, and get there in the least amount of time with the least amount of altitude loss. So the important thing is to get these coefficients A, B, and C from the parabolic equation. And there's a formula I'm probably simplifying it by leaving out the wind here. The optimal velocity is the square root of c, that number you got from the equation, plus the air sink speed divided by a. And once you figure out the units and do that, you can put that in an Excel spreadsheet, and it tells you, okay, I got a thermal that's going up at 3 meters per second, I'm in sink that's going down at 0.8 meters per second, and I need to go, 3 miles with no headwind through the sink with this airplane, and it will tell you where on that polar you want to fly. So now you can model the course. You know the sink rate of the airplane, you know the climb rate of the thermal because we have logger data. So we know how long it takes to climb from the bottom where you enter it up to the top where you can't see it anymore. You know the velocity of the airplane to get from here to here because that's from the speed to fly equation. So you know how long it takes you to get from here to here. You know the sink rate of the air in between the thermals because you measured it, again, off of historical logger data. And you know the sink rate of the airplane because it's off the polar. So now basically what you do is you can set up a course, for example, made up of these legs. Each one of these legs can be, say, and you can pick whatever number you want to set up the course based on historical data. You can say, okay, I know it's 3 meters per second climb, and it's 0.8 meters per second sink in between these two, and I know the distance between the thermals is 3/4 of a mile. And I know how long my course is. So I'm going to go to the chalkboard here. So I can say, okay, given that kind of a day, I know I have a 15-mile course, and I'm going to climb out at the launch up to here, and then every time I fly, I know how far it is to the next thermal, I know how long it takes me to get up here, I know how far it is to the next thermal, I know how long it takes me to get here, I know how far it is here, I know that, and I know that, and I want to cross the finish line with 200 meters left so that I don't hit the wires on my way to the landing circle. So this is your model. This is basically one long Excel spreadsheet equation, given all this data that you put in. So now, what you can do is each airplane that you design has a polar associated with it. And there'll be one polar for the speed mode, one polar for the cruise mode, one polar for the thermal mode, and you can use those to put in different inputs for A, B, and C for those coefficients. So I can take a design for Philip Cold, I can blow up the Supra, I can blow up the Bubble Dancer, I can put in Mark Drela's Bubble Dancer, I can put in an F3B airplane that I blew up that I got from somebody, I can put in my old Epler 374, I can put in R&R's MXC, I can put in their SDXC, because I know what all those airplanes are, and I can generate a polar for each one. And then I can just generate a massive spreadsheet and race all these airplanes against each other. And one of them's going to be 90 minutes, one of them's going to be 93 minutes, one of them's going to be 98 minutes, given a course. And it just falls out the other end, and you can say, okay, I want to make it 10% smaller. Is it going to get there sooner, or is it going to get there later? Because you're going to have to trade how high you can go on that triangle. If you make the airplane smaller and take an inch off the cord, now you can only go to here. So you're going to either have to be a little more careful on your way over here so you don't end up too low, or you're going to have to fly, it's basically going to be a different polar to get over there. And you're going to come in lower, which means the other thing you can do, you can even make this as complex as to say the lift gets bigger as you get higher up. So I'm going to put a line right here, and in my Excel spreadsheet formula, everything below here is 1.5 meters per second climb rate. Everything above here is 3 meters per second climb rate. And this is a bit of a simplification, but it reflects the fact that the lift does get stronger as you get higher. And I know that because I have measured logger data on my climb rates, and you can see that if you can get up into that 700, 800, 900 meter air, the lift gets stronger. So now the bigger core has an advantage because it's spending more time up in this area than the smaller core that's spending it down here. So now you can vary the course model. You can cap the altitude with a haze or an inversion layer and say, okay, you can't go over 700 meters or it's going to go out of sight, or you've got different air sliding over coming from the coast or whatever that's killing your lift. You can only go 700 meters. So a different airplane is going to win in that case. You can add a wind speed and see what happens when you're going up against a headwind the whole way. You can vary the thermal and sink strength. You can vary the distance between thermals. Say in the morning, if you want to take an early course, it might be 2 meter per second climb with almost negligible sink in between, and your thermals are only half a mile apart. You might get into the afternoon air where you've got some, and I've measured this, basically the conversion was like 16 miles an hour lift rate. The airplane's going up at 16 miles an hour. Really, really good thermal. It's frightening to get up in that good stuff. So you can do that, and your sink rate in between is very high. There's big sink in between, and your thermals are 3 miles or 4 miles apart. Which airplane's going to win in that case? You can vary the overall course distance. You can do a 5-mile course, a 9-mile course, a 15-mile course, a 45-mile course, and again, different airplanes going to win depending on whether it's a short course or a long course. The smaller airplanes going to be favored in the short course because you're not out there as long and you can get there and back again with less altitude. So you build a spreadsheet for each course and you run all the candidate designs through it, and given that course history, one of the models you're looking at is going to do better than all the rest and win more of the races. That's the one that you're going to want to go with. Or you could say, all right, I'm going to build 2 models, and this one I'm going to fly on the really light days in the morning, and this one I'm going to fly when it gets real heavy and big lift and big wind and have to go really fast. Gordon Jennings, I don't know if you know Gordon Jennings, he's another flyer down in St. Louis, Missouri. He took this a step farther to something I don't know how to do, but he said I could use something called a Monte Carlo simulation, which is basically where you put in thousands of different course models. And you set up a computer program to generate an Excel spreadsheet for each one, and it gives you a cloud of solutions. Each one, is going to give you different solutions, and wherever the density of that cloud is, that's the design you want to pick. That's a little bit beyond where I want to go. As an exercise, it would be interesting if you knew how to do it. I don't know how to do it. So I got some structural considerations for this airplane that we're working on from Mark Drela. He has a PDF explanation for everything you could ever imagine. What's the stress? How do I design for the spar? This or that. You put it out there, and he'll send it to you. Cutting holes for servos in the wing requires a spar to carry the load across the gap. That's not 100% absolutely guaranteed, but as a rule of thumb, I don't like to violate that, especially when you're going to be flying the kind of stuff we're flying. Construction for practical reasons, we went with a bag wing with carbon fiber wing skins, a socked spar with a carbon fiber wing sock, and pultruded carbon caps. It's very easy to build. It's versatile. You can make it any size you want. You can do it on your kitchen counter. You don't need any fancy equipment, and it's really, really strong. For the design of the structure, there's this program I got that a few guys have put input into. Jay Decker, a friend of mine, a guy named Popper, I think his name is Vincent over in the Netherlands, added some to it. Joe Wurts added some to it. Basically, you can't really see it here, but basically you're putting in the thickness of the wing, what kind of skin, what kind of fabric, what kind of spar, how fast you expect it to go, how many G's you expect to pull out at, and it will spit out a graph like this that gives you a load curve right here, the red line, and the blue is the is the carbon skin strength as compared to that aero load. And you're basically trying to keep the majority of that over the red line, or at least match to it. If you had a cutout in your wing, like I was describing for the servo, and you had no spar, what you would essentially have is a gap in here where it would come down, and that's where your wing would break. And I have run these through, and this is pretty accurate. And it gives you a wing that's not going to break, that's pretty strong, and you're not overbuilding it or underbuilding it. The end result, we ran through several different airfoil families from Philip Cole, and then once we settled on a family of airfoils, we varied the size quite a bit. Smaller plane versus bigger plane, and whichever one won the most counter races on paper is the one I ended up building. Structurally, I did have it clocked at 164 miles an hour with a pullout at Montague, and it survived. It has a pretty good contest record. Depends on who's on my team. If I can get Bob McGowan to fly my team, we generally win the contest. With some other people, we do okay. There's some luck involved, a lot of strategy involved, but the airplane is quite good. What we're seeing now is that the courses are tending to be shorter and shorter. There are no more open distance races. The shorter course, if you run it through the spreadsheet, tends to favor the smaller airplane. This one is still competitive. If you're looking at like 30 to 40 miles, in the 9 to 15 mile courses, the smaller airplanes are starting to look better. So we've got one of those on the board. Here's the plane that came out of this design effort. This is a Philip Cole design. This one actually has the Philip Cole design fuselage, which he said is very important. It's his wing and his tail. It's Mark Drela's structure, and it's Joe Wurts' contribution on how to design the race and then have the airplane come out the other side. One thing that Philip Cole told me that I didn't realize at the time, you can see this is a very skinny fuselage. It's like almost like a TV plane, as opposed to the big fat fuselage that I showed in the previous photos. He told me that effect is 10 times more important than anything you could do with a wing compared to the Super.
What's the chord width on the wing?
This one I think is an 11 or 12 inch. Let's see, it's 300 millimeters, which is
12 inch, thereabouts. 11 or 12, 11 and 12.
300 millimeter.
12 inches.
Which is, this is a medium-sized airplane. There are guys flying Explorers in this event. Philip Cole flew something even smaller than that and won. So that seems to be the trend. I've gone bigger and won races with it, but the races again are getting faster and faster all the time. So the airplanes are getting smaller and smaller all the time.
Is it an illusion, or is that fin and rudder really that tall? It looks really high.
It's about 14 inches.
So it's not that bad. It's an illusion.
I think it's an illusion in the picture, but it's not undersized, certainly.
Yeah.
You design the tail for these not for flying, but for the launch. Because you've got a 5 kilo, 4 meter airplane that needs to be flying when it leaves your hand, and it needs to be stable when it leaves your hand. And if you push the limit on the tail, where it would fly fine, but it's marginal on the launch, you're asking for trouble when it leaves your hand. I've seen them go in like that. So this is what we're flying now. What we have on the board is this fuselage with a Royale wing, which is a little bit smaller chord. And the Drela foils, which are 99% as good as this for cross country. The wing loading will go up. The maximum altitude will come down a little bit, and we'll keep this airplane for the long course and fly that airplane in the short course.
What Drela airfoils are you using?
AG 40 series.
Okay.
The super ones. The XC8, which was the poly version of this, that used the AG 23 to 27 or 28 series. That's off the bag bubble dancer design. Those are designed to work without flaps and ailerons. Very simple.
Well, wording was 35, 36, 37.
No, none of these, since the first one I showed, the white ones, are the same foil all the way out. Because the Reynolds number changes quite a bit as you go from the root to the tip.
Yeah.
And there are two considerations. One is the Reynolds number changes quite a bit as you go from the root to the tip. So generally, you tend to go thinner. You tend to pull the high point forward, and you tend to reduce the camber a little bit as you go from the root to the tip. And in this case, what you're doing is you're accounting for the Reynolds number, and you're building in the washout into the airfoil without having to cut any twist into it. The other consideration you have as you go from the root to the tip is that you can play tricks with the airfoils and get a tighter turning machine that will fly straight line fast and turn very well without dropping a tip by changing the airfoil as you go from the root to the tip. And I can tell you that Mark Drela is probably the best in the world at doing that. I don't know what he does. I'm not at that level, but he is really, really good at it. There is out there a 4-meter blown up Supra that was in between one of these designs. I don't own it. It's Bill Murray's airplane. And I can tell you, I've put a couple hours on that plane, and it is one of the sweetest flying, best handling airplanes I've ever flown, ever. I mean, you can tip it right up on a tip and circle really tight at 11 pounds. And yet it will go 90 miles an hour. It's just, and the handling on it is absolutely beautiful. You can come to a thermal at 300 meters, take it up to 700 meters, do cubinates until you're back down to altitude, and then thermal out again. I've done that over and over again in Sacramento. It's an amazing flying airplane. And it's just stock Supra. It's like Mark knew what he was doing, and until someone comes up with a better method of designing, you know, he designed the tool for designing it, he designed the airplane, it's going to be hard to beat. But Phillips' airplane is very, very good. Very good. And it's a little bit faster. That's what we gain with this. Because what did we give up? Why did we go with this? We gave up a little bit of thermaling to make it go faster compared to the Supra. And if anybody's interested, I have some threads here. These are threads I've done on aircraft design. They take a while to read through, but I kind of go into detail about some of the spreadsheets and the modeling and stuff like that where I got it.
Greg,
Yes.
what are you using for controls on that airplane?
Okay. On this airplane, I will reveal all my tricks. You know what I'm doing. I have flaps, ailerons, rudder, and elevator. And I am using a little bit of differential. I am mixing aileron to flaps, so the whole trailing edge moves. The inner part moves about 1/3 as much as the outer part. I have 5 flight modes. There's launch, speed, which is a little bit reflex, cruise, which is the natural airfoil, thermal, which is a little bit of camber, and then low save, which is more camber. That's the one you pull out when you're at tree height. And literally, last time I was on course with this very airplane, we got into a position where there just wasn't any lift, and my co-pilot was flying around and around and around, trying to find lift here and there, and basically he got to the point where he was going to have to let it land. And I said, well, let me land it. And I felt this gust and whirlwind come around the car, and I said, well, let's try it. And I was at a height where I could not have pop the wires to land on the other side where there was a better field. I had to land on this side of the telephone lines. And I caught the thermal and went out on it in low save mode. And it went out, I was really surprised. And it was fully loaded. So we're talking about like, 30 or 40 feet. Yeah. You don't want to get there when you're racing because that racks a lot of time up on your course if you're low and scratching. But if you need it, it's there. So I've got low save mode, and then I got launch mode, which is even more camber and only up on the ailerons, not down. And in launch mode, you go to full rudder mix, so that you got a lot of throw and a lot of power when you're launching it. Each mode has its own elevator trim, and it has its own aileron rudder mix. So for example, in speed mode, contrary to what I would do on a DLG, I jack the aileron to rudder mix up quite a bit. Because basically I'm running down the road, and if I make an adjustment, I want to be able to steer it without banking a lot. And I got that from Bob McGowan, and it works very well. Cross country is a little bit different from TD or hand launch in how you would set it up for the modes or in the mixes. And you basically just play with it until you get what you want. So again, this is a full house, 6 servos, 4 servos in the wing, and these are JR high voltage wing servos. I have one of those at the root of the fin that goes up to the elevator pushrod, and I have the rudder servo right here ahead of the wing with a carbon pushrod that's all internal. The fuselage is just big enough at the end that I can fit the whole linkage inside and nothing's exposed. So this airplane has RDS, Bowdy's RDS on the wing. The elevator linkage is buried in the fin, and the rudder linkage is buried in the fuse, so there are no exposed linkages anywhere on the plane. And you can tell it's slipperier than the one with the bigger fuse and the horns hanging out the back.
Fuselage got sound drag.
Yes, this fuselage I got from Philip Cole, and what I did is he has an old version of XFL5 that will give you the wireframe, and by magic of luck, I was able to just take those points and put them in a CAD program, and it worked. And it made a wireframe model of this fuselage. And then I made little block solid models of every component, the servos, the receiver, the batteries, everything. And I just stuck those in there and made sure everything would fit, and it did. So then I took the wireframe model and I sliced it in sections and printed out cross sections of each station and glued it to a cereal box. And then we made a plug using a wooden dowel and a carbon tube with blue foam on the outside. We just made it oversized and then started sanding it down to fit the cardboard templates. And then we glassed it and made a mold on it. So we have a mold for that.
I call it cardboard aided design.
Serial.
It works.
So you said
Yeah, for sure.
you don't have any washout in the wing, but your aerodynamic washout,
Right.
you're going from a high camber airfoil at the roof.
It's not a high camber, but it's kind of like a Supra.
They're
Yeah.
relationship to each other.
You lower the camber as you go from the roof to the tip.
You lower the camber.
Yes.
Okay, I think it would be the opposite.
No, that gives you
Some
that
people do it that way. I've seen Joe Wurts do that.
Yeah.
Hand launch. And you have to know what you're doing, and I don't know what they're doing.
Because your tip sweep will also have an effect on where your high points would be.
Yes. This one is done with no sweep. It's basically pipe perfect from the top view. And you want that because you're trying to make a straight spar or a reasonably straight spar. Starting here,
Oh,
you
your trailing
lower-
edge is not straight then?
the trailing edge is not straight.
Oh, okay.
The spar is straight,
Okay.
or reasonably close. So the camera goes down a little bit as you go from the root to the tip. The high point comes forward as you go from the root to the tip.
Right.
And the thickness goes down as you go from the root to the tip.
You use the same airfoil to run?
In relation to the leading edge, in other words, it could be straight all the way across, but because the leading edge is coming shooting back, that point is moving forward. Right?
Well, the high point is about,
That's what I mean.
yeah, the high point is about straight, pretty close to straight. Basically what you're doing is trying to
Yeah,
make your hinge line straight.
right.
You tweak the position of the airfoils to make the hinge line straight. I was going to say,
When Philip was here
Yeah.
a year ago, I told him, I talked to him about one thing, the tendency to fly too slow. I see a lot of, I'm a full size, but
oh, right.
to keep the speed so that you're up on the boulder. You don't want to be if you get too slow, you're going down the side. You're going to be losing.
That's something we found out by running through this polar, is when you run the speed to fly, you find out you might want to be up in here, which is faster than you thought you should be flying to get through the sink. But it actually gets you there at a higher altitude because you got through the sink faster. Which is why the airfoil is not designed necessarily for minimum sink like you might design a TD plane. Right, it's not a floater. You want to pay very close attention to what the polar curve is doing up in here. Because it might look really good down here where you're trying to scrape out your last bit of lift, or make that 7 or 10 minute flight, or make that 15-minute flight and float it out, get out on that morning thermal. But that's not what we're doing here. We're racing. So the shape of the curve up in here gets more important, and it doesn't take much of a shift in where this line is to affect the race results in the end. You might have two airfoils, and if you were looking at them down here, like, oh, this one's just like that one, you find out they deviate up here, and you might pay a little bit down here and gain much more up in here.
So how do you differentiate what's different about cross-country flying versus TD flying? I mean, we're still trying to transition between thermals as well, but are you looking at, because it's longer distances between thermals, because your altitudes are higher?
As far as the flying, yeah, but if you were to model, and I'm sure Joe Wurts and Mark Drela have done this, you can model a TD contest just like you modeled the cross-country contest, but you're not going to pick the same variables. Visibility is probably not going to come into your equation at all.
And you're trying to maximize the time, not minimize it.
You're trying to maximize the time that you're in the air. The speed that you can get from A to B is not irrelevant because you might need to punch through some headwind to get there, but it's not going to be as important as it is here. And the other thing that's going to come into your equation that's very important in TV that's irrelevant in cross-country is the launch. So you need to figure out what are your variables, what are your equations that are going to affect your launch. How high are you going to get on the toe? How much can you get off the ping? How hard is it to top out? And how much can you get extra? Is it going to carry? Those are going to all of a sudden become very important.
True distance is not an issue.
True distance is not an issue, or it's not weighted very high.
Yeah.
So basically, what you do in this Excel spreadsheet is you figure out how you want to weight things. What's more important, this or that. And again, you do the same thing in TD. How much do you want to weight that launch? It might be a big factor. An extra 100 feet might make a big difference in your hang times. So yeah, you would do the same thing, but you would come up with a different answer because it's a TD airplane. And again, the size would affect that. If you're looking at F3J with a hand tow, there's another thing even beyond TD, which is their toe is part of the window. So they want to get out that line as fast as they possibly can. So now you're steering to something that you want to tow with as little time as possible and get up as high as you can. So you're going to want to decrease the mass, you're going to want to decrease the drag, and you're going to want to make it slippery enough that it pings off that springy line in a second and a half with a lot of speed, and then you can convert that into altitude or to get where you want to go for that thermal. It's essentially line-assisted hand launch.
And all your launch mode or flight modes are all switches. There's no trim
I don't use a slider anymore.
slider.
Back before the SD10G, I was flying Vision, and those I would use the sliders. And you just had to know where you were there. I think it worked just as well. Honestly, you could fly this race with an Aeronautics Vision and never be hampered at all. And not use any switches. It would all be on the slider. You can do the same thing with DLG. You can, but you're looking at, again, different factors. You've got your acceleration on the windup, you've got the maximum velocity when you let go of it, you've got the pull out to go to your vertical climb, which is important. You've got the drag on the climb. You've got to look at your tip versus root airfoil and planform and try to minimize your rotational inertia to get the swing down after that initial launch. And you're basically trying to weight that as compared to the handling of the airplane in the air and the straight line velocity, the sink rate. Again, it's just a different spreadsheet. But you would use the same method. I've done this a little bit with DLG. I'm not an expert at it, and I know Mark Drela's taken it farther. And I've never really dug into his analysis deeply. But the last DLG I designed, I did use some of these little tricks here. I was pretty happy with what came out. It's not as good as what the factories are turning out right now, but it's not bad. It did what I wanted it to do.
Right. Do you look at different airfoils for different speed ranges?
Absolutely. Yeah, for this exercise, my company was shut down Thanksgiving, a few days of Thanksgiving, a few days of Christmas. I basically pulled up in an apartment and pulled every airfoil that had published polar or published coordinates off the internet that existed that might have fit. I looked at F3V airfoils, I looked at everything I could get from Norbert Habe, I looked at MH, I looked at Drela, I looked at stuff that I got from Philip Kolb, and there is some variation out there. Some things do work better than others. But I covered everything I could get a hold of.
I'm going to start calling you Dr. Norseman.
Not quite.
Okay. Thank you, Greg.
All right.
Thank you.